things. So, okay, let me first tell you that it's really a pleasure for me to be here in Chennai, but those who know me know that it's true, otherwise I wouldn't be so often here. And especially a very big honor and pleasure today and this week because of this conference. I must say that if you're looking at the title, I thought I was really an outsider in it, but it was told to me that really, and Balu said it also, that essentially we were celebrating the 60th birthday of Ram, and so Ram, I understand also that your birthday is spreading over the time, and so I wish you many happy return of the year. Okay. So, well, I would like to talk about the density of some automatic sequences, and in some way I chose this because there's some collaboration with also some Indian mathematician in it, Chantal Ashram on the one side and Tanga Durai on the other, and I'll tell you about what it is. So I think I should say a few words about automatic sequence, although people here in Chennai have some idea about what it is. But let me go quickly to what is automatic sequence. So Q is an integer, which is at least 2. Essentially, we are going to write integers in the base Q. This is what it will be helpful for. Yep, this is not the right one. I'm going in the... Sorry, I have to get acquainted with this. When I am acquainted, possibly it goes better. So what it is, you have an oriented graph. This is oriented graph. That is to say that you have vertices, finite number of vertices, and you have edges or arrows, which are orientated. You see there is an arrow on it, and they are numbered between 0 and q minus 1. So from each point, you have exactly q outgoing arrows. Okay, and you have also a finite set. So one of the state is the initial state. Usually we call that R0. If we number the states are R0 up to Rs or something like that, this will be the R0. And then you have a finite set of the outputs, which is just a finite set. And to each state, you have a way to associate one arrow. Here it is 1-to-1, but it need not be 1-to-1, and indeed in interesting cases it's not 1-to-1, but well, it makes life a bit more difficult, but this is how it goes. So what is the use of this? Essentially what we do is the following. We write an integer n in the base q, so epsilon k, q to the k, and so on. We may discuss about proper or improper representation, but as regards automatic sequences, there's no point about making a difference. The automaton may be a bit different, but it will be the same thing if you allow proper or improper representation. So what I am going to use is something which works both for proper or improper representation. That is to say that if you have 0 at the beginning, you don't care much about it. So what you do, you have then, once you have an integer, you have a word of elements on the alphabet, which are the numbers between 0 and q minus 1. And to n, we associate an element of O. And this element of O, the output, will be called A of n. So if A is the automaton, and it's obtained in the following way, you start with the initial state, the R0, and then you read epsilon k minus 1, and so on up to epsilon 0, and each time you follow the arrow with the given number. Okay, and then A of n is just when you have finished reading all the digits, then A of n will be the image by tau of the last state which is met. So let me go back to the examples I was drawing. What is the first one doing? The first one is doing the following. You start here, and so you see that this will be in base 2. You have only the digit 0 and 1. This is in base 2, and you start with this state, which will correspond to the value 0, and then you read the digit. So you see that each time you are reading a digit, which is 0, you do nothing, wherever you are, and each time you are reading a 1, you are just changing from one state to the other. So what will be the output? The output will be 0 if you have an even number of 1s in the development expansion of n in base 2 if you have an even number of 1, and if you have an odd number of 1, you meet this value 1. So this is really the basic automatic sequence, and if you want to test something about automatic sequence, start with this sequence, which is known as the 2-Morse sequence, so it is more than 100 years old. This is another one which will be also of interest for us. This one is in base 3, and you do the following. You start with a 0, as long as you see a 0, so we are reading from the left. As long as you read a 0, you stay here. This is why, by the way, the fact that on the initial state you have always this loop with a 0 means that you will not be dependent on the fact that your representation is proper or not. Because if you start by putting some 0, you simply do nothing. So you don't care much. You are staying on the initial state. Okay, so you stay on the initial state, and if you see a 1, you are going here. And then whatever you read, you stay here. And if you see a 2, you go here, and whatever you do, you stay with the number 2. That is to say that this automaton is just reading what is the first significant digit in the word n. What is the digit of the highest value, which is either 1 or 2. So this sequence is an automatic sequence. Okay. So now I need something about the density of the elements. So a sequence of elements in a finite set O is just said to be Q automatic. If there is a Q automaton A such that UN is obtained by this automaton. So this, for example, the sequences which tells you what is the first significant digit in n in base 3, but you can do the same thing in base 10 or whatever you wish, is an automatic sequence. You can do it also in base 2, but in base 2 this is not that interesting. I'll let you understand why. And so this is Q-automatic sequences. Now, if you have a Q-automatic sequence, an element O, you can look at all the integers n such that A of n or UN is equal to the element little o. This is called the fiber. So in some way, your automatic sequence will be a certain sequence of O1, O2, and so on, and then again OI, OJ, and so on. And what you are looking at, given O, you are looking at all the integers which go to this value. For example, the fiber associated to the value 1 for the digits for the second automaton will be the integers we start with a 1 in the base 3. The fiber over 0 for the 2-Morse sequence will be the integers for which the number of ones in the 2 expansion is even. Okay? This is the way it goes. So now there are the question, of course, if you have a sequence of integer, you have notions of density. There are several density. We'll be essentially interested in 2 density. One which is the asymptotic or natural density. You count the element up to n, you divide by n, and you see whether there is a density, whether there is a limit or not. It may exist or it may not exist. If it exists, this is called the natural density. And you have a weaker form, which is the analytic or logarithmic density. There are different ways to present it. You count the inverse of the elements. Forget about 0, this is not very important. The inverse of the element. So if you have everything, it will give you something which is log n. So you divide by log n, and so you have something which is between 0 and 1. And you look at the limit, and again, this limit may or may not exist. But this is a weaker form for limit, because just by partial summation, it's easy to see that if you have a natural density or asymptotic density, then you have also a logarithmic density. Okay? So the main question, and now you understand maybe about the title, about density of automatic sequences, will be to say something about existence of such limit. You may also have existence of this, but this is an old result. And so I start with the theorem, maybe. So the theorem, due to Cobham, this was at the end of the 60s, so it's more than 40 years ago, showed that if you take any Q-automatic sequence, then it always admits a logarithmic density. And as regards natural density, you cannot expect always for an automatic sequence to have a natural density. Just think of the integer which starts with a 1. Think in base 10. we were more acquainted with base 10, it's clear that if you go to something which is 2 times 10 to the k, at least 1/2 of the element, we start with a 1. But if you just go to something which is 10 to the k, at most 1/9 of them will be, so there is no natural density, this is clear. And by Cobham result, but you can of course do it with bare hands, there is logarithmic density for those integers. So this is also the fact that automatic sequence does not have always a natural density. And so what I want to discuss a bit is a few examples in which we try to prove that there is a natural density. This is the question. Okay, now there is also a useful sufficient condition for a Q automatic sequence to admit a natural density. Possibly Martine, if she is around, can tell me whether there is something better than anonymous. I think this is something which is more or less basic. I give you the weak version. There is a slightly stronger version according to the fact that you are already acquainted with those things or not. If you are not acquainted at all, then there is some nice way, which is to say, when you see the graph of your automaton, on the graph of the automaton, you have a sufficient condition for a density to exist. This is the following, that there exists some integer h, such that when you have any pair of states, you can go from one state to the other one with exactly h arrows. So maybe I can come back to this. Okay. So this is the case here. Definitely, you can go from this to this. You see, this is easy. In some way, you have a loop here, and this is quite easy because you can go from this one to this one, and you can go back. So in I think 2 steps, you can go from any state. No, even in 1 step, you can go from any one to any one. Yeah. Okay. So and here, this is not the case because you see that from this state, you cannot go back to this one. And from this state, you cannot go back to this one. If there is only one element like that, it's not too bad. So if you know about something about, for example, Markov-Chain, this is exactly the same thing, except that here it is deterministic, but it is exactly the same thing as for Markov-Chain. In some way, you say here that with probability 1/2, you stay here, and probability 1/2, you go to this one. So it's really the graph of a Markov-Chain. So if you know something about classification of the states, then it will tell you that this is a final class. And so if you have only one final class, and this final class has the same property I was saying, that is to say it is positively regular, then you are in a good condition. So if you know about automata or Markov-Chain, it's fine. Otherwise, you just take for granted this theorem, and I give you some hint of the proof. It's not very difficult. You look at the transition matrix. So the transition matrix will just tell you how many arrows you have from one state to the other. So you count the number of states which go from Rj to Ri. You call that Mij. You divide by Q because each time you have Q arrows that goes out. And this is a nice stochastic matrix. And if you want to be in a good situation, of course, you are going to iterate this. And what is important is that essentially in this matrix, you have only one. So one is always an eigenvalue because it is stochastic. All the eigenvalues are at most 1. But if you are in this nice positive situation, Perron-Frobenius tell you that there is only one eigenvalue of one is the only eigenvalue of modulus 1, and it is simple eigenvalue. So then everything will collapse and everything will go on the same vector. So this is the trick why you have this. So essentially, once you know Perron-Frobenius, you have everything. Okay, so now I go to 2 problems I want to talk about. Essentially, I think I will spend most of the time on this one. Not exactly this one. This one is more or less hopeless. Is the sequence 3/2 to the n uniformly distributed mod 1? So for those who know what it is, it's fine. For those who didn't know, I will tell you a way to see it, to express it. When you have an integer, when you have a real number, you take this fractional part. This is for the fractional part. That is to say that you forget about the integral part and you are just interested in the decimal part. Okay, you keep the decimal part. For example, if you take 3 over 2 to the 1, then this will be 0.50000, of course. And you don't care about the fact that 3 over 2 is 1.5. You forget about the 1, you just keep the 5, 0.5000. This will be what you get. Now the point is to know what can you say about the frequency where epsilon 1 of n is occurring. What about the frequency where epsilon 1, the pair epsilon 1, epsilon 2 is occurring? And so we would say that the sequence is uniformly distributed, mod 1, if you can prove the following. Each time you take a block of elements between 0 and 9 of length s, when you take the sequence of n such that epsilon 1 of n, epsilon 2 of n, epsilon s of n is equal to b, then this sequence has a natural density which is equal to 10 to minus s. I mean, this is what you would like to know to say that this is uniformly distributed mod 1. Well, it's not, this is not known, and very little is known about the distribution of 3 over 2 to the n, and so even, well, you can talk about Piso-Vijayarana numbers, but essentially, let us say, we know almost nothing. So I'm going to look at this problem in a simple context. So the context is the following, that in some way we want to forget about carryover. If you have thought a bit of that problem, you understand that really the mess, it's quite easy to multiply. Once you have this sequence of elements, to multiply it by 1.5, even if you look it in base 2, it is even easier. Then what you do is just to add you just shift it and you add it. You shift and you add, and the real problem is carryover. And so carryover is a mess, and so you want to get rid of carryover. So I'm just looking at a very much simpler problem than this problem. And I don't think it will help in understanding what is this problem. It's just sort of motivation. We don't know how to do it. We do something simple. So our frame will be the following. What were integers will be polynomials. I prefer to write them polynomials in x minus 1 because this will be the integral part, and since I am interested in the expansion, I prefer to have positive exponent in the expansion. So this is why I consider the integers as that is to say, instead of considering my expansion in base 10, for example, I am writing it in base 1 over 10. And so 10 will be 1 over 10 to minus 1, 100 will be 1 over 10 to minus 2, and this is why I prefer to put the negative elements here and the positive one there. As regards the fraction field, there is no difficulty. This is the same one. This corresponds to rationals. Then you complete it, and you get Lorentz series, and this is a completion, and you can understand it as being something like R. There are many things that are connected with that. And what will be R over Z will be just when you take when you suppress the integers. So you are taking formal power series, and except that the 0 is better to consider as being in the polynomial. You can also shift it as you wish, and I will describe it by using the word cusp, which is maybe the only connection with the official subject of the conference. And then you have this representation. Every real number, now, Lorentz series, may be expressed with the final part, which is negative. This will be the polynomial part. Polynomials means the integral part. And then you have something which will be the fractional part, which is in R over Z. Okay? And we say that n is decimal if its expansion is finite. Exactly in the like in the usual case. And the notation is this one. So we have to get a bit familiar with that. So I will write out some example. Maybe it's okay. Right now, definition, what will be the distribution mod 1. So distribution mod 1 will be the following. What you do, you take a block of length x, s, exactly the same thing as what we were doing in the real case. And we consider the sequence of integers for which alpha 1n, alpha 2n, alpha Sn, that is to say when I have this number and I raise it to power n, I just consider the first S digit of eta to the n, and I say I'm counting the number of elements for which it is b, and then if this has a density, we say that there is a distribution. And if this density is 1 over q to the s, each time we say that this distribution is uniform. Okay? But it may have a limit, and then we say that it has a distribution. Be careful, in the real case, it's slightly different if you want to define really what is to have a distribution, because you have always this representation of, if you just take integers, you can also approximate them with elements where you have blocks which are 99999. So you have to be a bit careful about this double representation, but in our case, this does not occur. But for uniform distribution, as soon as the density is continuous, it's fine. Okay, and so this will depend on the density you are considering. So let us look at one example. I take theta, which is x to minus 1 plus x2, and I try to look at the powers. So theta to the 0 is 1, that is to say that here you have just the element 1. X minus 1 plus x plus minus 2, so this is x minus 1. You have no constant term, you have x and you have x2. So this will be the representation of theta. And then you start to work with bare hands and compute the powers of it. Okay, at some point you are a bit, by the way, this is something, I started to do that in Kingston in '79 for possibly the first time we met. Because it was rather hot and I was in a room with no air conditioning, so I was essentially trying to compute stupidly some things instead of trying to do mathematics, but very quickly mathematics will come out. So, okay, so just to give you, for example, about notation, so this will be the digit corresponding to the 7th element in theta to power of 5. You see, this is the way it is done. So this is this arrow you have, and you fill it. So maybe we start to do some mathematics. How you go from one line to the other? Well, to go from one line to the other, you do the following. You are multiplying by x minus 1 plus x2, so it's just some shift and you add. That's what I was saying, except that here we are in a good position, there is no carryover. So you are just looking what will be this element. Since you are multiplying by x2, in the previous one you have to find one which is 2 steps before. When you multiply by x, you take this one and you take the one which is 1 step before. And when you multiply by x minus 1, you take this one. And so this will be 1 plus 0 is 1. Okay? Here you go on. This is 1 plus 0 plus 1. So 1 plus 1 is 0 and this is 0. Okay? And you can go on. It's a bit boring. But you go on and you find this, which is rather remarkable. And then when you start to see something like that, you say, well, there should be some good reason why it is like that. And of course, the good reason is what we never teach to students because it's too good. It is called the freshman's dream, which is a plus b squared is a squared plus b squared. Here it's even better. It's a plus b squared is a plus b. But, okay. So, which means that indeed, when you go from theta to theta squared, it's not too difficult. Each time you have a 1, you replace this one by 1, 0. This 0 will be 0, 0. This one will be 1, 0. This one will be 0, 1. Okay? So each time you are just squaring like that. So you go very quickly to theta 4. Theta 4 will be just the same one. This one will be 1, 0. This 0 will be 4, 0. This one will be 4, 0 and a 1. This one will be 4, 0 and a 1. And again, you go that way. So in some way, you have a lot of places where you go how it goes, and then you can in some way reduce it so you can go quicker to that. Okay. So to understand what we are saying the following. I start with some element which is theta to the n. And I try to keep track of a few elements which are the elements in x minus 1, x0, x1. And I don't know what is the coefficient of x minus 3, x minus 2, and x2. But if I square it, I know what it will be, because this v will become of 0 will become a 0v. This w will become a 0w. And this element u will become a 0u. So when I'm squaring, I am winning something. I know more elements than I had a priori. So a priori, you start only with the coefficient of those elements. When you square it, you know that it will be better because you are introducing zeros. And even this one will be a 0 also, but I don't need it, so I didn't write it. But now if I am interested in theta 2n plus 1, then I know what I do. This element, I can find it out because it is with this one plus this one plus this one, and this is u plus v. This element here will be u plus v plus 0, this is u, and this element will be 0 plus v plus w, and this is v plus w. So it's rather nice because if as soon as you know the 3 elements for theta n, you know also the 3 elements which are this one for theta 2n, and you know also them for theta 2n plus 1. So what you can say is the following. If I have something at theta to the 2n which is uv dot w, dot is the decimal point, you see, after the x to the 0. If I have something which is uvw, then if I double it, I get something which would be 0v0. I forget about the other ones. I'm not interested much. I just keep them in memory because they will be used for the 2n plus 1. Then in theta 2n plus 1, the first digit will be u plus w, the second one will be u, then you have the decimal point, and then you have v plus w. Okay? So what does it give? It gives the following, that I recall here that I have this way, that when I start with uv dot w, if I do it with 2n plus 1, I go to 0v0, and by 2n plus 0, and by 2n plus 1, I go to this one. Forget about the 2n and just keep the 0 and the 1. We are starting with something which is theta to the 0, so it is just everything is 0 except x to the 0. So you have something which is 0, 1, 0. And now when you square it, you stay on the same one. When you double it plus 1, you go exactly to theta. And so you see this one, this one, this one. You even don't have all of them, but you don't care. And then you go back. I mean, each time with a 0, 2n plus 0, you go somewhere, and with 2n plus 1, you go there. So essentially, what you are saying is that the sequence of those elements is automatic. Fine. So this sequence is automatic. We are just interested maybe in the first digit, but of course the first digit, you get it by projection. If you project it, and you see that you have to project it, what will be of interest is not really to have this element, but to have 0 here, and the 0 which is here, and this one will be projected to 1, and this one will be projected to 1. Okay. And this is quite useful. For example, you want to compute theta 1 of 799. You see, if you remember what we were doing on the, by computing all the elements, it takes a certain time to do that. I want to show you that this is really an efficient way for computing, that we are really doing something automatic. So the hint is to write it in base, well, when I was saying 799, I was thinking that this was 799 in base 10. You write it in base 2. And now what you are going to do is just to do the following, that reading your digits one after the other. So it's exactly the automatic procedure that you are doing. So you read the digit one after the other. So you start from here. You have a 1. You have another 1. You have 3 zeros. 1, 2, 3 zeros. And then you have 5 ones. 1, 1, 1, 1, 1. You stop here. And this means that theta to the theta 1, 799 is equal to 1. So it's quite efficient way. And of course, you can use it also to prove a few things. I would like to do it. So this one, maybe I should say something here. This one is quite easy to understand if you are, again, acquainted at least with Markov chain, if not with automatic sequences. You understand what happens, that I had to be a bit careful not to fall on 0. So essentially, almost whatever you do, you fall on the 0, because once you are in a 0, you are trapped, and you cannot go out of the 0. So you have just this element, and the fact that you have this which is just the final state, the final class has only one element, and this element corresponds to 0, this means that indeed the density of the theta 1n, the density of those for which it is equal to 0 is equal to 1. So you can get from that immediately at least the fact that the density exists, and the density exists, n is equal to 1 if you are interested in the element which is 0. Okay? So you prove something that the density exists, at least for the first digit. I mean, if we knew something like that for 3 over 2 to the n, we would be so happy. But, well, okay, so I look at the other one. It's not always the case yet that you fall on 1. This is why I wanted to give you another example. It is x minus 1 plus 1 plus x. So again, you do the same thing. You will try to square it and to, yeah, I think time is going on, but it's fine. So you have a transition matrix. Well, if you know, yeah, I explain what is the transition matrix. It turns out that this one has the property that for some power, it has only strictly positive element. Again, you can go from any element to any element, and since you have a loop, it's very nice because this loop permits you, if you can go from anyone to anyone, whatever the number of steps, you can always go through this element and step on it, you see, and so you can show that you have a positive matrix. And you look at what is the eigenvalues. There are 1 and 1/2, and the eigenvector associated to 1 is 2/3, and then you can prove that way that this set, the set of for which you have a 0 as a natural density, which is 2/3, and for the other one, the natural density is 1/3. So it has a density, and this density is not uniform. If it had to be uniform, it would be 1/2 and 1/2. Okay, there are good reasons why there is it is never uniformly distributed. All that has been worked out. I just give some of the statement. The complete statement are more technical. This was done, you recognize the 79 because this was, by the way, in the proceedings of this, maybe not of this conference, but in any case of this year. Maybe the Durham conference that was following. So if you take theta to be decimal, then the sequence theta to the n has always a natural distribution mod 1, and this distribution is never uniform. If you wish to ask question after that, I tell you why it's not uniform. And we extended that with Jean-Paul Alouche after that, and showed, and this is in part in this thesis, that if we take theta to be algebraic over fq of x, then the sequence theta to the n has a logarithmic distribution mod 1, and which is never uniform. We know a lot more about that the support of the distribution has Hausdorff dimension 0. So it's really very rare that it can be Dirac at the origin and so on and so on. We don't know everything. And for example, we don't know about the natural distribution. You see, this is, in the case of decimal, we have a natural distribution. In the case of algebraic, we only have the logarithmic density. And this is what we are working on now with the Tangadurai. And so this is some work in progress. I tell you what is the difficulty in some way. Consider this, which is for x1, x minus 1 plus 1 plus x to the n. This was the automaton that was giving you the first digit. Now, if you want to know what is the automaton that gives you the two first digit, of course it is connected with this one. But situation can be bad, because even if here you have a density, it may be that over this one you have two elements, and each of which is attained with no natural density. You see, the fact that you have a density for 0.1 may come from the fact that you have 0.10 with only logarithmic density and 0.11 with only logarithmic density. And of course it may happen that the union of two sequences with no natural density has a natural density. So this could be a bad case. And what we show with Tanga is that this is not the case. That is to say that if we are in a good condition here for the first decimal we can meet, I mean in general, but I am taking on this example, then of course here you can see it, because above 0 you have 0, 0, 0, 1. Not everything is above 0, but it's clear that if you have a 1 that goes from this to this, whatever you start with, if you go from a 1 you have to go to this one. So in some way, those automatons are rather well connected. And what we could prove is that indeed, if this one is nice, then all the ones which are above are nice also. So although you have in some way to check something on infinitely many automata, you can just figure out from one automaton, if you are in the good case, then everything will be in the good case, which is a nice thing, except that we made some experiment, and each time we noticed that we are in the good case, maybe in the good case where there is only one finite class, but well, always we are in a good case, but we cannot prove that up to now that we are always in a good case. So there is still some work to do. So it's just some partial answer, but I wanted to tell a bit about that. And I still have some 2 minutes or something like that. And so I want to say something. Theorem is that I'm pretty sure it's true, but I mean, well, okay, better to be prudent about that. Several cases where it's great, but okay, Chantal Ashram, I hope it is true, but just be prudent for that. So we are interested in this time in the least significant digit of n factorial in base B. This has been studied by several people, starting, I don't know if any of it was a start Kakutani, and a lot of people have been working on these kind of things. Decimal, smallest integer, significant integer of 10 to the, in n factorial in base 10 or something like that. Okay. So this element is different from 0. Then the question again, it's quite easy to show that it's not completely obvious because we're not dealing with n, but with n factorial. So to know that this is an automatic sequence, you have to work a bit, but not too hard. I mean, it's basically coming back to Lagrange, to Legendre, or something like that. You see, the number of 0, you can express it with the sum of the digits of n in base B. This is the result of Legendre. There's a formula that tells you the number of zeros here can be expressed with the number of zeros of n in base B. It's a bit more complicated than that, but basically it is that. And this is why it is automatic. Somewhere. So knowing that it has logarithmic density is just straightforward. I mean, this is Cobham, but then you have to work a bit on knowing what can you say about this automaton so that you can prove that it has a natural density. And this is what we are doing, and I think it's just the time to stop. So thank you very much. And again, happy birthday, Ram, and welcome to the club.